Okay, the first learning objective in PS2-1, which is all about forces, is that I can represent forces on an object as one-dimensional vectors. So the basic idea is that you can represent them, which represent them for our case is going to be drawing the forces. So another way of looking at this is I can draw free body diagrams. This is a very specific skill in physics called free body diagrams, and that's what we're going to be focusing on. First off, before we start, we need to understand what a force is. And very simply, a force is just any kind of physical push or pull. It's just anything that pushes or pulls an object is a force. Forces are vector quantities. That means they have a direction and a magnitude. We've talked about this before. Velocity is a vector quantity. Acceleration is a vector quantity. Displacement is a vector quantity. All of these are vector quantities. Some terminology for vectors are the tail and the head. So the tail is where the vector starts, and the head is where it is pointed to. It's the head of the arrow tip. The unit for force is called a Newton, of course, named after Sir Isaac Newton, and is represented with just capital N. Now, Newton isn't a base unit. It's not the most simple unit. In fact, there are units that are inside of a Newton. So a Newton is actually a kilogram times a meter divided by a second squared. There is a reason I color coded it blue and red here. When we get to Newton's second law, this color coding will become very obvious. Let's discuss what a free body diagram is. So free body diagrams are sketches designed to model the forces acting on an object. To the left here, you can see an example. Here we have a box on a sloped ramp. There are two forces acting on this box. There's the force of gravity going straight down towards the center of the earth, and then there's the normal force. This is the force pushing back up because it's in contact with the ramp. Notice here that all of the vectors are starting from the center of the mass of the object and pointed in the direction that they are pushing the object. Here are some simple rules for drawing free body diagrams. The first rule is to identify the system or the object that you're interested in. We're only going to be drawing the forces for the object that we are currently interested in the motion of. And then we're going to draw a simplified sketch of the system. So by that I mean we're going to draw the object and its immediate surroundings that are coming in contact with it. If we go back up to this diagram right here, we notice we drew the box, which is the object we're interested in, and we also drew the slope because it's relevant to this problem, because the slope is touching the box and is causing the force. Now notice, we're not including any forces acting on the slope. We don't care about that, because what we care about is the motion of the box, not the slope. Second step is that we're going to identify what forces are acting on the system. So we need to identify the forces and make sure you can actually identify the source of the force. If you don't have a good justification for why the force should be acting on the object, then there's a good chance that that force doesn't actually even exist. Let's apply this second rule to this situation right here with the box on the slope. We know that there's gravity because it's a box on Earth. So there's going to be gravity. If you're on Earth, there's going to be gravity, guaranteed. However, this force right here eludes a lot of students. Why would there be a force? Well, we can also think of it this way. If there wasn't this normal force pushing back up, then there would only be one force, and that would be the force of gravity going straight down. And if there's only one force acting on this object should start accelerating in the direction of that force. But it can't do that because this slope is here. The reason this object stays in one position is because the slope is pushing back up on it. You could think of a person standing on a scale that's measuring their weight. The reason this works, the reason a scale could measure your weight, is because you are pushing on the scale, and the scale is also pushing back up on you. So here I was able to justify the reasons for why these forces must be there. The third step is you're going to draw each force with the tail of the vector at the center of the object and the head pointing in the direction of the force. Again, if we go back to our example, notice all tails are at the center of the object and moving towards the direction of the force. The fourth step, we're going to draw the vector forces with relative lengths. So in other words, A force that's twice as large needs a vector twice as long. If we had a box and one force was acting to the right and a larger force was acting to the left, we need to make sure the larger force has a larger vector. All right, let's apply this example to a box. So we have two forces acting on the box. One force is pushing with 20 newtons of force towards the right, and the other is pushing with 40 newtons towards the left. We're not going to need it, but it's always good practice. We're going to call going to the right as positive. So therefore, going to the left is negative. It's not going to be relevant for this problem because we're just representing the forces with a free body diagram, but it's always good practice to start there. So let's start with the force going to the right, 20 newtons. I'm going to draw a vector about that long. We could even label this F1 maybe. And we could say it's equal to 20 newtons. And then we have one going to the left that should be roughly double the size of this. It looks to be about double the size. We have 2 equals 40 newtons. Notice we drew the box. We drew the force. We recognized what forces are acting on it. The problem gave us those. And then we drew the forces with the tail at the very center of the object and then pointing it in the direction that they are going. Another key thing was we drew these vectors with relative lengths. The one that was twice as big of a force needs to be twice as long. Let's apply this to another example. So in this example, we have a ball attached to a string and it's being tossed around in a vertical circle. So vertical circle meaning that gravity is still acting on it going straight down. So there should be a gravity force going down in this example. Let's draw the free body diagram. So for this one, first off, let's just draw gravity because we know we're going to have a gravitational force going straight down. But then is there any other force? Well, there'd have to be another force to keep it going in a circle. And also, we know where that source of the force is. That force is going to be from the string, and it's going to be in the same direction that the string is going. So we can draw a force vector for the string. Now we have no information about the relative sizes of these vectors. So we're going to draw them roughly around the same length. And we can label these. This could be the force of gravity, and this could be the force of tension. Here is your practice. Draw the free body diagram for a tug-of-war game. So in other words, you have 2 people, at least, on either side of the rope, and they're pulling them. One's pulling it this way, the other one's pulling it that way. So draw the forces such that the left side is winning. So you're going to have to think about the relative size of these forces. Second problem is draw a free body diagram for a person dragging a box by a rope. The rope is making a 30-degree angle with the ground. Assume that there is friction with the ground.